Hey, Michael, I had a question real quick.
Yes, Brandon, what is your question?
All right, so how do you distinguish whether it's a common gate, common drain, or common source? Is it what's connected to ground?
I mean, that's in the small signal model, yes, it's connected to ground, but it's sometimes hard to tell if you're looking at the complete discrete circuit with DC biasing and everything. It can be hard to
Mm-hmm.
tell.
Mm-hmm. Yeah,
So,
I was having some trouble in the homework trying to distinguish it.
well, the ones in this homework were all common source because we hadn't gotten to the common gate and common drain yet.
Okay, okay, cool. Thank you.
But let me share my screen briefly, and I guess I'll include this part in the recording too, because some people might have the answer. Okay, Brandon. So if we go here, if we go to, let's see, common source amplifiers, go back a few slides to slide number 71. Slide 71 basically says, sure, you can think, okay, source is connected to a DC supply, gate is connected to a DC supply, drain is connected to a DC supply, hence the name common source, common gate, common drain. However, easiest way I've had teaching students how to identify them is look for the input and output is. Common source amplifier, the input's between gate and ground, output is between drain and ground. Common gate input is between source and ground, output is also between drain and ground. And then common drain amplifier, the source follower, input is also called between gate and ground like the common source, but the output is now between source and ground. These are the easy ways. So if we look at our discrete amplifiers, here we can see the input signal is fed into the gate and the output across the load is taken from the drain, common source amplifier. That's how I would identify 75 in like, I don't know, 5 seconds. The discrete common drain discrete source follower, I guess, yeah. On slide 81, input goes into the gate, output is taken at the source, must be a common drain amplifier. 5 seconds. Discrete common gate amplifier on slide 85, input goes into the source, output taken at the drain, must be a common gate amplifier. Does that help you, Brandon?
Yeah, that does. Thank you.
Cool. That just bad so much stuff click. Did I go too fast through them, Luke? Is that what you're saying? Or you're saying that like something clicked in your head and now you understand it? I don't know. I'm being very much a low social IQ engineer and not figured out what you mean. Oh, it makes sense. That's good. That's what I want. Riyadh, I just exposed the Michael Hayashi quick trick to identifying the different types of amplifier. So common source, common drain, and common gate. What's the trick? Doctors don't want you to know. Click this ad and find out. I'll give you the quick trick once 950 rolls around. Pull from alpha. It's going to use Alfred, I guess. So. We need to encourage more of our classmates to show up. Yeah, everything in homework 1 was a common source amplifier. I am pretty sure. Pretty sure. No one actually asked me about problem 7. or at least part B of problem 7. Yeah. We hadn't gotten to the common gate and common drain amplifiers by Friday, so I was like, I wasn't going to include them on the homework. If you want to know my philosophy for teaching this class, again, it's a hard class, my goal is to be demanding, but not cruel. It's up to you to determine how true that is. But I'm demanding, but I try not to be cruel. Contrast that with the philosophy of some of the professors who've taught this class prior. And, there's definitely a contrast. What is a Smith chart? A Smith chart is a really cool nomograph, which is a very fancy word that means, collection of grid lines that helps you solve certain types of problems because it has the equations embedded into the structure of the chart. It is used to solve reflections and transmissions on transmission lines and in other places where you have, reflection transmission type ideas such as in optics and acoustics, things like that. So it is a fancy chart that allows you to, graphically solve for reflections and transmissions on. Are you going to use it in 304.11? Oh, someone said yes. I did not actually use this chart in 304.11. I think I used it one day in 604, which is the graduate version of 304.11. It's a really cool thing. It looks neat as a wallpaper and stuff like that, but it's we have computers nowadays, which are going to give you more accuracy. All right, man, another fairly small class. Where is everyone? Okay, so according to the question that was asked by Brandon, what is the trick for quickly identifying a common source, common gate, and common drain amplifier? Slide 71 holds the key. Common source, inputs between gate and ground, and the outputs between drain and ground. Common gate, input between source and ground, output between drain and ground. The common drain amplifier or source follower, input between gate and ground, like the common source amplifier, but the output is different. It's between source and ground. So we can quickly go to all these discrete common source amplifiers where the DC biasing arrangement sometimes, confuses the connections of things. And we can see quickly that here the signal is being fed through the coupling capacitor into the gate, and we're taking the output across the load resistor from the drain. Must be a common source amplifier. So that's 75. I go to slide 81, the discrete source follower. Input goes into the gate through a coupling capacitor. We take the output from the source through another coupling capacitor. Must be a common drain amplifier. Common gate amplifier on slide 85. We can see input goes into the source through the coupling capacitor. Output comes out of the drain through the coupling capacitor. Must be a common gate amplifier. So in 5 seconds each, I could determine what these amplifier configurations were. No problem. That's the secret. I don't know. When I taught this course previously, I did exam questions that were worth 20 points each. Usually you got 2 points if you could correctly identify the type of amplifier. So just write down, CG amp or CD amp or CS amp, that got you 2 points. So we'll see if that persists into this semester. All right, everyone's here. We're in a brand new lecture set. Makes me happy. So here's lecture set 2, ordinary differential equations for circuits. We covered a little bit, but I want to refresh our memory. So we went over ODEs. We're going to go over ODE solutions today. We're going to talk about the basics of ordinary differential equations. We're going to decompose it into a homogeneous solution and a particular solution, and then we'll put them together for the complete solution. In the future, we will talk about the first order circuits, resistor capacitor and resistor inductor circuits. L stands for inductor, probably because it's named after Lenz, but no one's quite sure about that. And then we have the second order circuits, LC circuits, and then the RLC circuit where you add a resistor. And then finally, we'll get into a little bit of what you need to do to handle switch circuits. So we talked about why study ordinary differential equations. Pretty much all of engineering uses ODEs in some capacity. It understands basically all of physics-driven phenomenon. We're only going to deal with constant coefficient linear differential equations, which makes our lives a lot easier than just dealing with the broad field of ordinary differential equations like you would in Math 266 or 366 or a course such as that. And then even though we're almost never solve circuits by direct modeling with ordinary differential, mouse is being very sensitive today, ordinary differential equations, it is crucial to have the background to understand how physical phenomena behave, and it's the backbone of the more advanced methods like convolution and Laplace transforms that will be studied in future lecture sets. So here is the structure of a constant coefficient linear ordinary differential equation. So it's going to have the following parts. So we see that we're taking a sum of constant coefficients, AK, these are not functions of time or anything, times each derivative, not raised to a power. So, we've got the zeroth derivative, x of t, first derivative, dx of t dt, second derivative, d squared, x of t, dt squared, and so on. So we've got a linear combination of derivatives. So the order of the differential equation, we're summing from the function itself up to n, where n is that order of the ordinary differential equation. It's synonymous with the highest derivative present. And we have this all equal to a forcing function called y of t. So we know that using functions of the form e to the at will be very useful to find x of t. Because when you take the derivative of e to the at, you get a times e to the at, which is just a scaled copy of the original function. And it's easy to add them together. You can just factor out the e to the at, each of the derivatives will have in common. So it makes it, quite simple, or at least the simplest way to solve for y of t. And in fact, we will see that this is the case. Pretty much every single function we look at is an exponential of some form or another. If you want to know why it's the exponential, like, a very, hoity-toity mathematical explanation is that, the exponential function is the eigenfunction for the differential operator. Or you can just say it has this nice property that when you take its derivative, you just get a scale copy of itself. Now we'll decompose the complete solution x of t, the function x of t that solves this differential equation, into two parts: the homogeneous solution x sub h of t, and the particular solution x sub p of t, such that x of t is equal to the homogeneous solution plus the particular solution. Is the diffie-q hard? Well, hopefully between any exposure you have in your differential equations class, which you've either taken or are taking now, and what we're going over right now, you should be able to hopefully be a lot more comfortable with this. Like I said, we're dealing with linear constant coefficient, so it's not like we're dealing with like the integrating factor method or method of variations. I think that's the term for it in ordinary differential equations. Like, we're going with pretty classical, straightforward characteristic polynomial-based methods. So, yay math. So let's talk about the homogeneous solution in particular and really zoom in on it. So another word for homogeneous solution is natural solution. Remember, it's x sub h of t. And we will find that it is an entire family of functions, probably x of x of t, that solve the ordinary differential equations in the absence of a forcing function. So that means we're setting the left-hand side of this ordinary differential equation to 0, and it stays at 0 for all time. So, okay, you might ask why we're doing this. And the answer is that the homogeneous solution is basically what arises due to the structure of the ordinary differential equation itself. What I mean by that is the certain linear combination of manipulations of x of t and its derivatives that lends itself to a specific homogeneous solution that is going to appear regardless of what forcing function we choose. And since it is going to appear regardless of the forcing function we choose to have, it's basically the initial step in solving any ordinary differential equation. So we're going to go through this process no matter what, basically. So it's definitely worth studying. And, I want to emphasize this last bullet point very carefully. So because the homogeneous solution, solves the differential equation when the left-hand side is equal to 0, and this is a linear differential equation where superposition applies, you can think of, well, the particular solution must be whatever it ends up being, but we can always add, this family of functions from the homogeneous solution to the left to, both sides of the equation. And, to the right-hand side, we're adding all of our families of functions. And on the left-hand side, we're adding 0. And because adding 0 doesn't change the left-hand side, we know that the homogeneous solution must always appear. I'll explain that one more time in a slightly different way. So we know that whatever combination of, derivatives and coefficients we have, the homogeneous solution will work, because when we plug it into the differential equation, it always produces a 0 result. So we can just keep adding this family of functions, and regardless of what's on the left-hand side, we know that family of functions must be there because it doesn't change our contributions to building the forcing function. Does anyone have any questions about that? Okay. I know I definitely wrestled with this idea when I was taking differential equations. So, but when you think of it as just adding 0, it's like, oh yeah, adding 0 is an identity type operation. It doesn't change your contributions towards building up y of t. So how do we possibly figure out what family of functions makes up the homogeneous solution? The answer is the characteristic equation method. So the characteristic equation of a ordinary differential equation is the polynomial that helps you find the homogeneous solution without relying on explicitly taking derivatives of x of t. So here's the process for how you would, prove what the characteristic polynomial should be. So we start with a homogeneous ODE. So again, it's from our definition of the constant coefficient linear ordinary differential equation, set equal to 0. So 0 is the sum from k equals 0 to n of coefficient a sub k times derivative d, or the kth derivative of x of t. Now, we assume that it's going to be of the form, we assume x of t is going to be of the form a e to the lambda t. So we plug that in for x of t, and we're taking the kth derivative of a e to the lambda t. Well, when you take the kth derivative of this, the a will stay out front. So all these terms will have a big A out front. We can factor that out of the sum. They're going to have, lambda times itself to whatever order of derivative we're dealing with. So if it's the third derivative, we'll have 3 lambdas times each other out front. And then we'll always have an e to the lambda t sticking around. So we'll have a and e to the lambda t sticking around, and then we still have our a sub k's, and now we have lambda to the n appearing. Actually, that is a mistake. I am pretty sure. Yes. It should be lambda to the k power. And in the next equation, it should be lambda to the k power. So, I proofread this like for an hour last night, and I still have an issue. We multiply both sides by 1 over a e to the negative lambda t, and that's okay because this is a finite quantity, and the only time it's 0 is at infinity, so it's not like we're wiping out anything by multiplying by 0. This is finite to non-zero. So when we do that, we're going to be left with 0 equals the sum from k equals 0 to n of a to the k lambda to the k power. Again, correction. And we notice this is a polynomial because it's just coefficients and powers of lambda. So it's a polynomial in lambda. Now, the shortcut way to do this, seen up here, is you just replace each or kth derivative of x of t with lambda to the k, again, correction, and the ODE instead equal to 0. So solving the characteristic equation using polynomial root finding techniques results in lambda k, or lambda sub k, where k is equal to 1 through n. Then the so-called natural frequencies associated with the homogeneous solution. So we get x of t is going to be this family of functions where it's a sum of unknown ak's times e to the lambda sub k of t. If anyone has a question, just shout out. Now we will see that there is an exception to this rule that will come up later. But for the first pass understanding of what's going on, we're going to get a linear combination of different exponentials where, the exponentials are different because they have different lambda sub k's in the exponent. Let's do an example so you can see what it is. And, unlike in lecture set 1, this example will be worked out entirely in front of you. So find the homogeneous solution to y of t equals 5 times x of t plus 2 times dx of t dt. So the slow way of doing this, and the way we'll do it at first, is just by guessing the solution form. So we'll do it like we did with the characteristic polynomial proof. We'll assume the homogeneous solution is a e to the lambda t, since oh man, another issue. Yeah. In the bottom of slide 6, it should be k equals 1 to n. Man, I was not careful. Because obviously I said k ranges from 1 through n, so you can't start at 0. So for this, we're going to assume that there is exactly one a coefficient and one lambda sub 1, basically, of t we'll just call it lambda rather than calling it lambda sub 1. So the homogeneous solution is going to be AE to the lambda t. We got to figure out what lambda is, though. So we're going to substitute the homogeneous solution into the ODE with y of t, equivalent to 0. So 0 is equal to 5ae to the lambda t plus 2 times the derivative of ae to the lambda t. Well, we can take this derivative rather quickly. This should be one of the easiest derivatives we can take. So we'll get 0 is equal to 5ae to the lambda t plus 2 times a times lambda times e to the lambda t. Now we can multiply through by e to the minus lambda t. We can also multiply through by 1 over a if we wanted, but we'll get 0 is equal to 5a plus 2a times lambda. We can solve this for lambda and get lambda is equal to minus 5 halves. So we rewrite the homogeneous solution x sub h of t as ae to the negative 5 halves t. And that is our answer. We can't say any farther what a is because, this is just a family of solutions at this point. So we can let a be any real number, basically, and that will work. Now, what about solution by characteristic equation method? So use the shortcut to find the characteristic equation. So we just take this and we'll set 0 equal to 5 times lambda to the 0 because it's the 0 derivative here, plus twice lambda to the first because it's the first derivative here. Lambda to the 0 is just 1. So we subtract 5, divide by 2, and we get lambda is equal to negative 5 halves. And then we write the natural solution as a linear combination of natural frequencies, which there's only one. So we just say x of h of t is equal to ae to the minus 5 halves t, where we've introduced the coefficient a at this point. And we get the exact same answer, though in much fewer steps.
If we're going to cancel out the a in the guessing the solution form, if we're going to cancel out the a anyway, is it necessary to have it? Because, well, when I was doing 266, that wasn't there.
So the short answer is, we assume that we need some coefficient out there. So it's not necessary to form the characteristic polynomial, but we know that the homogeneous solution must have the a there. If you're doing it like the 266 method, like you would, get your dx's on one side, your dt's on the other, and then you would integrate, and then you would raise to the eth power, so you would get e to the constant of integration out front, which is the same as having a capital A.
Yeah.
Does that answer your question, Pranav?
Yeah.
And the second is lambda to the 0 equal to lambda to the first? No. Negative 5 lambda to the 0th is equal to 2 lambda to the first. The coefficients are very important to keep. We don't have to derive it every time, though, right? Absolutely not. Like, I use the shortcut basically every time for the rest of, this course. The shortcut is so much faster. Beyond. So, and again, we cannot find those coefficients a sub k from the ODE alone. If you want to figure out what those coefficients are, we must have a, physical system described by an initial value problem, or IVP. So I'm introducing a little bit of, differential equations language here. So an initial value problem consists of two things. The first being the ordinary differential equation that the system obeys. We've been doing that in, the previous 5 slides. And then the second thing is we must have the initial conditions that the solution must fit. So initial conditions are usually written as, the value that the function must take at time equals 0. The value that the derivative must take at time equals 0. The value that higher order derivatives take at time equals 0. Now you can specify them at other times. However, almost always they're specified at time equals 0 for our own convenience and because that's how problems are structured. So now if I say find the solution to the homogeneous form of y of t equals 5x of t plus 2 dx of t dt with x of 0 equal to 3, now we can eliminate the ambiguity of the coefficient a. So we'll find the natural solution as before. So if we use the shortcuts, 3 steps to get x sub h of t is equal to a e to the negative 5 halves t. Plug in our initial conditions. So at time equals 0, xh of 0 must be equal to 3 because we're finding a solution to a homogeneous form. And then equals a e to the negative 5 halves times 0. And, I would argue, we have reached the biggest danger of the course. Maybe not the biggest danger of the course, but like certainly a biggest danger of, this lecture set, I can say. Remember, e to the 0 equals what? E to the 0 equals 1. So e to the negative 5 halves times 0 is e to the 0, which is the same thing as 1. So we're saying a times 1 equals 3, or a equals 3. So we can use our homogeneous solution and now just rewrite it, plugging in a equals 3 and get x of t equals 3 times e to the negative 5 halves t. And congratulations, it's just numbers there and a function of t. I cannot stress to you how many times people will do the differential equations right, do the calculus right, but then struggle with the actual evaluation of e to the 0. So be wary of that. Yeah, anything to the 0th power other than 0 itself and infinity. Okay, anything other than 0 and infinity to the 0th power is equal to 1.
So why didn't we use the evaluation in the first method? We could say that a equals 0, right?
You could say a equals 0. Well, a could also be 1 or negative 1 or 3. If you say a equals 0, you've basically eliminated this entire thing. So you don't know what a is equal to. You have to figure it out. Until you're given the initial value problem, you don't know what a is. Siad, first, what if your guess for each of the lambda t is wrong? What if it is actually sinusoidal? We'll get to that later on. But remember, e to a complex values, call it j theta, is equal to cosine of theta plus j times sine theta by Euler's identity. So you can get sinusoids by saying it's still exponential, just with imaginary values. So 0 to the 0 equals pi. Sometimes it's one of those indeterminate forms. Those 7 indeterminate forms will not leave your life once you get out of calculus 1. Sid, do you go by Ali? Yeah, you can type that. All right. Now we finished talking about the homogeneous solution and we moved on to the particular solution. So the particular, or also known as the force solution, x sub p of t to an ODE, is the family of functions that solve the ODE for a given forcing function y of t not equal to 0. So now we don't have y of t equal to 0. We have the given y of t plugged in there. The particular solution is associated with the functional form of the function applied to the system. So, the particular solution is, the parts that solve the differential equation because we chose a very specific forcing function. Because of that choice of forcing function, we expect something that looks like the forcing function to appear in the output as well. In this sort of linear constant coefficient differential equation case. Now, a point I need to emphasize: we cannot find the coefficients to the solution in an initial value problem until both homogeneous and particular solutions are found. So you can't try to find coefficients ahead of time. Those A's, we were using A sub K's. You have to wait until after you have both the homogeneous and particular solutions. So I'm giving you a cheat sheet right here, where we assume a functional form that matches the general functional form of y of t. So the problem is always, what does it mean to match a general functional form to an input? So I've kind of explained it here. So say y of t is equal to 17 u of t. What is u of t? Well, think of it basically as something that behaves just like a constant for this point in time. It's the step function. We haven't gotten to the step function yet, but basically it's turns on and then it stays constant. So then we just assume that the particular solution is some coefficient b times u of t. So we don't know if it's going to be 17 as b, or 5 or 3 or -3 or 1 or 0 or 2, but we know that it's going to be something that has this sort of step-like behavior, that looks like a constant that's just been turned on. If y of t is 17e to the negative bt, then assume that x sub p of t is equal to b times e to the negative bt. We can expect a, some, scaled version of the same exponential that appears. And by same exponential, I mean it has the same, negative b times t structure in the exponent. If you get y of t is equal to 17e to the negative bt plus 13e to the positive bt, then you assume x sub p of t is equal to b1 e to the minus b of t plus b2 e to the plus b of t. So, this is a linear operation. We can treat each of this. So we'll get something that's, a copy of e to the minus bt, and then some other coefficient times e to the positive bt. You broke it up linearly. Now, mathematicians would be like, okay, we'll have x sub p is equal to c1 hyperbolic cosine of b of t plus c2 times hyperbolic sine of bt, where hyperbolic sine and cosine are defined as a linear combination of e to the minus bt and e to the plus bt. Since they're both linear combinations of the same functions, we could rewrite it using this different basis instead. We're not going to use this very often because a sort of quick rule of ECE 20002 is that exponential decay is cool, exponential growth is lame. We don't like exponential growth. So we're not going to use exponential growth functions very often, just because of the nature of the problems we solve. And then lastly, if y of t is equal to 17 cosine of omega t, then we must assume that the particular solution is b1 cosine of omega t plus b2 sine of omega t. basically, if we apply a cosine, we're not sure about the phase, the actual delay of the function introduced. So we must have both cosine and sine components. The alternative way of thinking about this is x sub p of t is equal to c times cosine omega t plus capital phi, where we have c and capital phi as unknown coefficients. Phi isn't really a coefficient, but it's an unknown. Regardless, always have the same number of unknowns to solve. Any questions to this point? I'm taking notes because I just thought of a good way to explain it. My GPA as time goes on is an exponential decay. Well, it's asymptotically approaching something. That's true for most people's GPA. It's asymptotically approaching dropping. Well, you just got to keep it above a 2.0 to graduate. So keep it above a 2.0. I'm trying to prevent people from dropping out. I don't want this to be, the weed out course that makes people quit. I want to hopefully teach people that this is approachable material, and you can do this. Yeah, that's the right attitude, Riyadh. GPA cap for ECE. Everyone's GPA is capped at 4.0. There's no going above it. All right, let's do an example with the particular solution. So find the particular solution to y of t equals 6e to the minus 2t u of t, which is in other words, you're saying y of t is equal to 6e to the negative 2t only if t is greater than 0. In the ODE, y of t equals 5x of t plus 2 dx dt. So we assume the particular solution. Unfortunately, unlike the homogeneous solution where we could use the characteristic polynomial and there's shortcuts, we don't get around that with the particular solution. So we have to do things the sort of hard way. There really isn't a quick alternative. So we have a forcing function that looks like an exponential. So we're going to say it's going to be b times the same exponential, same u of t tagged along at the end. Units of that function, purists rejoice that we're dealing with it early. So we'll substitute x sub p of t into the original ODE because it must satisfy the ODE, by itself, by linearity. So we'll get y of t, which is 6e to the minus 2t u of t, equals 5 times x sub p of t, which is b e to the minus 2t u of t, plus 2 times the derivative, which is, of b e to the minus 2t u of t. We'll take the derivative. So we'll take the derivative of, well, b is just a coefficient. We factor it out. Now we just need the derivative of e to the minus 2t u of t. But again, we're solving for t greater than 0. So we'll just think of it as, bringing a minus 2 out front. So 2 times minus 2 changes our coefficient out front to minus 4. So overall, we get 6e to the minus 2t u of t plus 5b e to the minus 2t u of t minus 4b e to the minus 2t u of t. And this is kind of messy. So we'll multiply through by e to the plus 2t and consider t greater than 0. T greater than 0 causes all of these u of t's to basically become 1. They go away from our equation. Multiplying through by e to the plus 2t, cancels out all these e to the minus 2t factors. So we'll get 6 equals 5b minus 4b. Hopefully this is all math that we're comfortable with. So we'll just get B is equal to 6. So we rewrite our particular solution from the original step 1, which is x of P of t is equal to plus 6 e to the minus 2t u of t. And there we go. That's our answer. Now, notice this whole thing, hinges on choosing the correct form of the particular solution. So that's why we have the cheat sheet on the previous slide. These are basically the functions we're going to deal with. There really aren't too many others that we encounter. If we need them, then we'll have to figure them out. Questions on the particular solution? Is this where we have to check for duplication? Yeah, we would have to check for duplication of, there are, a functional form that matches the root of a characteristic equation. We're getting to that. So everything is only mostly a lie, or everything is only mostly true. Life is only mostly a lie. But on slide 11, we'll get to how to handle that case. Things are still mostly true. Life is mostly a lie, though. So now let's talk about the complete solution. So by superposition, again, exploiting the linearity of the differential equation, we can combine the homogeneous and particular solutions back together to get the complete solution x of t is equal to x of h of t plus x of p of t. So only now can the initial conditions be applied to find the unknown coefficients. So, once we have the complete solution, now we can resolve the coefficients from our homogeneous part. And, as a rule, it takes n differential, or an nth order differential equation requires n different initial conditions. So if you have a third order differential equation where the highest power or the highest order derivative is x to q, the third derivative of x appears. That's a third order differential equation. Then you need n initial conditions. So 3 initial conditions, usually x of 0 or x0, x at time equals 0, dx of t at time equals 0, and d squared x of t dt squared at time equals 0. It's going to be a mouthful to keep track of all the little parts of the differential equation. So these initial conditions are often embedded into a circuit diagram rather than being explicitly stated. So, for us, the circuit diagram is going to say, okay, what the initial conditions are and what the ODE is. So we sometimes have to imply it from certain things being stated or not being stated. So as a special case, if the characteristic equation has a repeated root, then the homogeneous solution must include terms with multipliers from the next higher term in the power series of t. So multiplier 1 becomes t, multiplier t becomes t squared. And so basically, if we had, 2 roots equal to -5/2, we would have, a1 e to the -5/2 t plus a2 times t, where the multiplier 1 became t, times e to the -5/2 t. We'll get to an example where hopefully it becomes a little bit more clear what we mean in a couple slides. So as a special case, if the forcing function is of the same form as the homogeneous solution, it matches any of the terms of the homogeneous solution, then the particular solution must include multipliers from the next higher term in the power series of t. So first we apply the special case to the homogeneous solution, and then when we guess the form of the particular solution, we must include the multiplier there. X prime, yeah, that would be a better way to say it. So I guess solution by ODE method procedure. So I guess the 0 step is, find the ODE of whatever you're doing and the initial conditions, find ODE and initial conditions. And then the first step is going to be obtain the characteristic equation of the homogeneous ODE. So again, that's going to be, that should be lambda to the k power in 0 equals sum from k equals 0 to n, a sub k of lambda to the k. We'll solve the characteristic equation to obtain the form that the homogeneous solution takes. And then next, we solve for the coefficients of the particular solution x of p for our given forcing function. And finally, we'll use initial conditions to resolve ambiguity of coefficients in the complete solution x of t. So we'll use these 4 steps as a guiding. We'll expand some of these because, the second step is usually a few steps and the third step is usually many steps. So let's see what we can do. Here is a complete solution example. Find the complete solution to y of t is equal to 5x of t plus 2 times the derivative with respect to t of x of t, with y of t equals 6 e to the minus 2t u of t, aka 6 e to the minus 2t, but only for t greater than 0, and x sub 0 equals 3. We've already done this before, except now we have to find the complete solution rather than just the particular solution. So the natural solution is, a e to the minus 5/2 t for reasons that we've covered in the last few slides. And the forced solution is x of p is equal to plus 6 e to the minus 2t u of t as before. Now we, do step 4, where we write the complete solution. X of t equals x of p of t plus x of h of t equals 6 e to the minus 2t u of t plus a e to the negative 5/2 t. From our initial condition, x of 0 is equal to 3, which must be equal to 6 e to the minus 2 times 0 plus a e to the negative 5/2 times 0. So we solve. 3 is equal to 6 plus a because e to the 0 is 1. Or we say a is equal to negative 3. So we rewrite the complete solution. So we took what we did in step 2 and we rewrite it, plug it in for a. Complete solution to the IVP is x of t is equal to plus 6 e to the minus 2t u of t minus 3 e to the minus 5/2 t. Notice, the coefficient a almost always changes from the homogeneous form IVP to the complete form IVP. Because before, when we did this on slide 8, we got that a was equal to 3. Now we get a is equal to negative 3. So, oh my gosh, the coefficient a changed. And that's because, you can't solve for the coefficient a early. You must wait until you have the complete solution form before you solve for a or any a sub k. So let's do a little bit more complicated example. So find the complete solution to y of t is equal to 5 e to the minus 5/2 t u of t in y of t is equal to 5x of t plus 2 dx of t dt with x sub 0 equals to 3. So it's the same natural solution as before. X of h of t is equal to a e to the minus 5/2 t. So now we see that our forcing function has this e to the minus 5/2 t in common with our natural solution. So our forced solution must use a multiplier of t. So x of p of t is equal to b times t times e to the minus 5/2 t u of t. This is in accordance with special case, the second special case on slide 11. So the next higher multiplier of t, or next higher power term in the power series of t is just t. So it's b times t times e to the minus 5/2 t u of t. So we substitute x sub p of t into the ordinary differential equation. 5e to the minus 5 halves t u of t is equal to 5b times t e to the minus 5 halves t u of t plus 2 times the derivative of particular solution. When we take this derivative, we must use the product rule because we have t times e to the minus 5 halves t u of t. So when we take the derivative with the product rule, we're going to get, a b out front of everything, and the 2 stays out front of everything. So we'll take the derivative of the first term, t becomes 1. So we're just left with the second term, e to the minus 5 halves t u of t. And then plus, we need the first term by itself, t, times the derivative of the second term. So we get a minus 5 halves e to the minus 5 halves t times u of t. So be careful with the product rule here. That trips up some people when you have these sorts of, matching forms. Multiply through by e to the plus 5 halves t and consider for t greater than 0. So we get 5 is equal to 5b times t plus 2b minus 5b times t. So we solve for b. Notice that the plus 5bt cancels with the minus 5bt. In general, you get these nice sorts of cancellations so that, b is never a function of t. Otherwise, it wouldn't be a constant coefficient linear differential equation anymore. That wouldn't make sense. And you get that b is equal to positive 5 halves. And for all this work, we are only halfway done. We only found the particular solution. We have to remember we were instructed to find the complete solution. So we write the complete solution. X of t is equal to x of p of t plus x of h of t is equal to 5 halves times t e to the minus 5 halves t u of t plus a times e to the negative 5 halves t. We apply our initial condition, x sub 0 equals 3. And we get at time equals 0, this entire term cancels out because it's multiplied by t equals 0. And then we get plus a e to the negative 5 halves times 0. So we just get that a is equal to 3. And we can rewrite our complete solution to the IVP as x sub t, or x of t equals 5 halves t e to the minus 5 halves t u of t plus 3 e to the negative 5 halves t. Okay. Hopefully we see how when we have the matching form that of our forcing function to our natural solution, we had to take that multiplier of t, and that made it harder when we had to take derivatives because we had to use the product rule and things like that. And then when we had to solve for b and then write the complete solution. Questions? All right. If there aren't any questions, we're going to do a harder ODE example. And this one I spent a lot of time on. Oh, what is the derivative of u of t? At this point, it is forbidden to talk about because it is the delta function, which we haven't talked about yet. However, note that we're only solving for t greater than 0, and the derivative of something that behaves like a constant is 0. So as long as we consider t greater than 0, we don't have to worry about its derivative. We don't need to worry any further about it. In the next lecture set 3, we will deal with its derivative much more formally and rigorously. Right now, we treat it like a constant. You are absolutely right. Agreed for lecture set 2 purposes. You're welcome, Aubrey. So here is a harder ODE example. So find the complete solution to 3e to the negative t u of t plus 4e to the minus 2t u of t, forcing function, equals 20x of t plus 24x dot of t plus 9x double dot of t plus x triple dot of t, where each dot represents a time derivative. So x dot of t is equal to dx of t dt. With the initial conditions, x of 0 is equal to 10, x dot of 0 is equal to -5, and x double dot of 0 is equal to 2. So we write the characteristic equation. So we say 0 is equal to 20, lambda to 0 is equal to 1, plus 24 lambda, plus 9 lambda squared, plus lambda cubed. And before you go and break out the cubic equation, note that we're dealing with nice, whole numbers. So we can solve for lambda with help from the rational root theorem. Recall the rational root theorem says that all rational roots of a polynomial must be of the form of all the factors of 20 plus or minus over all the factors of 1, because you take the constant term over the coefficient of your highest order term. So rational roots will be of the options plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20. And you get one of them, you can do polynomial long division to get, 0 is equal to lambda plus 2 quantity squared times lambda plus 5. Or you get lambda is equal to -2 with multiplicity 2, and lambda is equal to -5. So because we have a repeated root, back on slide 11, we applied the first special case, and we get that the natural solution is a1 e to the minus 2t plus a2 times t e to the minus 2t plus a3 e to the minus 5t. So this was a big step for us. So partial credit awarded. So assume a particular solution using the higher multiplier t. And we notice that, the first part of our forcing function is okay. So we'll get a b1 e to the minus t u of t. However, this e to the minus 2t u of t matches the e to the minus 2t terms of our homogeneous solution. We've already used multiplier 1 and t, so now we need a higher multiplier of t squared. So we'll get x of p of t is equal to b1 e to the t u of t plus b2 times t squared e to the minus 2t. So we substitute x of p of t into the ODE and take derivatives with the product rule. So we get left-hand side equals 20 times particular solution plus 24 times derivative of particular solution, where since we had t squared, we had to use the product rule once. And then once we have that term, we can add 9 times its derivative. So here we use the product rule twice for this middle term and for the final term. And it gets a little bit messy, so I already started grouping here. We have to add the derivative of it. So here I already grouped things out based off of the derivative of these two terms grouped together, and then the last term groups as such. So we simplify the equation and consider t greater than 0. We get this, and notice, oh my god, everything canceled. That was a multiple of t or t squared. So we solve by b1 and b2 by matching coefficients. So here we say 3 is multiplied by e to the minus t. So here we get that 3 must equal to 4b1, or b1 is equal to 3/4. And that 4 should be equal to 6b2 by matching coefficients of e to the minus 2t. And we get b sub 2 is equal to 2/3. Another big step. This is a lot of work. But we're still not done yet. We need to find the complete solution. So x of t is equal to our particular solution plus our homogeneous solution with a1, a2, and a3. So we need to find the derivatives of x of t in order to use our initial conditions, which involve x dot of 0 and x double dot of 0. And, we're using the product rule all over again. It's messy. Same for the second derivative. It's messy. And then now you would apply your initial conditions. So, you would get x0 is equal to 10 is equal to 3/4 plus t is equal to 0 here plus a1 plus t is equal to 0 here, and t is equal or 0 in the exponent, so that's just 1. So we get 10 is equal to 3/4 plus a1 plus a3. And then you do more grouping, and you get x dot of 0 is equal to -5 is equal to this expression, and x double dot of 0 is equal to 2 is equal to this expression. We can move all the constants to one side, all the multiples of a1, a2, and a3 to the other side. Write it as a matrix because we're, getting pretty exhausted at this point. And, now we can matrix solve this system of linear equations and get a1, a2, and a3 such that we write the complete solution to the initial value problem as x of t is equal to 3/4 e to the negative t u of t plus 2/3 t squared e to the minus 2t u of t plus 190 over 27 e to the minus 2t plus 188 over 9t e to the minus 2t plus 239 over 108 e to the minus 5t. And lo and behold, we are finally done. Don't say that I never did a problem as hard as you would see on homework in the lectures. This is definitely as hard as anything I would ever be willing to ask. Just because it is so many steps, it required so much of knowledge of algebra and differential equations and calculus. With that, you might be a little scared. That's a natural reaction, but are there any questions? Only have to use the rational root theorem on exam, or will the functions be easily factorable quadratic rule? I would say you should be prepared to use rational root theorem. It'll make your life a lot easier because sometimes you'll be given a cubic, not just in this lecture set, but later on down the line, or a quadratic equation, and being able to figure out which roots are there will help make your life easier. Why doesn't the multiplier apply to the first x sub p term? Because there's nothing that matches e to the minus t in our step 3, our third step of this problem. There's nothing that matches e to the minus t. So by linearity, we can say, okay, there's nothing that matches. It's allowed to stay the same. However, by this term matches 2 of the terms, so we need a t squared in front of it. Hopefully that answers your question from Aubrey. David, big math flex. Will this come on the exam? Like I said, you won't see anything harder. Once one's all algebra mistake and it's over, that's why we have partial credit. Our exam is going to be multiple choice. No multiple choice. All workout problems under fractional mercy. No. I would say, things that involve these sorts of nasty rationals numbers, probably not going to see that where you have to, set up a system of linear equations that this hard to solve. Like, you're not going to see that. Any more questions? If not, I'm going to recompile lecture set 2 to fix the mistakes, upload it, head to office hours, and make sure things are good. Unfortunately for me, I can't keep working ahead on lecture sets. I have to grade, which is fortunate for you that I start grading your homework. With that being said, thank you. Have a wonderful day, and I'll see you tomorrow. Goodbye, everyone. You're welcome. Goodbye. Bye-bye.